Niels Bohr proposed his model of the hydrogen atom in 1913. Over the next decade, it became increasingly clear that the wave-particle duality of light also applied to matter, and that electrons in particular have wave-like properties. This idea was the origin of the quantum mechanical model of the atom. Now, before I talk in more detail about the quantum model of the atom, I want to recapitulate some of the important properties of wave behavior. So we're familiar with waves in our everyday life on the surface of bodies of water. We're familiar with sound waves in a room or outside. And we're familiar with vibrations of things like guitar strings and drum heads. And all of these things embody the basic idea of wave behavior, namely that a wave is a disturbance in something. This something could be anything from water level in a pond to air pressure in the atmosphere, or electromagnetic field in the case of light, or any number of other things. Also, a wave doesn't have any definite location. It fills up the space that it's in, but it can be contained. The waves on that pond there are contained by the edges of the pond. Sound waves in a room are contained by the walls of the room. Vibrations of the head of a drum are contained by the edges of that drum head. Another property of waves is that they are more intense in some places than others. So if you look at the waves on the water there, there are some places where the waves are higher, other places where they're lower, and the same sort of thing applies to sound waves and vibration waves. And then the last thing that's going to be important to us is that waves interfere with other waves. And this is something that we're going to be returning to in a later video. So I want to look more closely at the specific example of a vibrating drum head to illustrate another concept that shows up when talking about waves. So when you bang on a drum, the drum head moves up and down, and that movement of the drum head sets up pressure waves in the air. Those pressure waves propagate outwards, but there are two different kinds of wave behavior that are going on here. The vibration of the drum head is called a standing wave. It's confined in space. It's not. It changes over time, but it's not spreading out in space. It's confined within a certain area. And by contrast, the propagation of sound waves form what's called a traveling wave, where the wave oscillates in time and also is moving through space. And for our purposes in discussing atoms, we're going to be interested in standing type waves. Now, wave behavior is something that was not obvious to physicists, and it's something that we don't experience in our everyday lives. And the reason for this is that macroscopic objects don't behave in a very wave-like way. They do have wave properties, but they're too small to really notice. And so something like a cannonball it's almost impossible to observe any wave behavior from it. It seems to move around like a particle. Even a mouse, which is much smaller, still is far too big to exhibit noticeable wave-like properties. And then even a bacterium, much smaller still, is still far too large to be able to notice its wave behavior. And even going much smaller, a molecule is still too big to really notice its wave properties. It's only when you start to get down to subatomic particles, like a proton, begins to get small enough and light enough that you can its wave behavior begins to become noticeable. And it's really only when you get down to electrons, which are 1,000 times lighter than protons, that you really start to notice the wave behavior. So electrons have much more noticeable wave behavior than protons. And one way to appreciate that is if you imagine a hydrogen atom where you've got a positively charged proton in the nucleus and then a negatively charged electron. If you were to put that electron in the nucleus or on the nucleus of the hydrogen atom, because the electron has a much lower mass, the wave of that electron would extend far from the nucleus of the atom. And if you were to sort of map out where this wave extends, it's sort of, well, I suppose technically it goes out to infinity, although it does fade away quite rapidly as you move away from the nucleus. And about 90% of the intensity of that wave appears within about 150 picometers of the proton that's in the center there. And the mathematical description of a wave like this is really outside the scope of this video, but I want to make it clear that the equations that describe this are very well understood, and they were worked out in the early part of the 20th century. And so with the proper mathematics, it's not hard to map out where an electron wave would be situated if you were to put it on top of a proton. You can also calculate how much energy that wave would have. And if you calculate the energy of an electron wave that's centered on a proton at the nucleus of a hydrogen atom, that energy comes out to be negative 2.179 times 10 to the minus 18 joules. And that number may look familiar. That's exactly the same energy as the ground state orbit in Niels Bohr's model of the hydrogen atom. In the Bohr model, the lowest possible energy that a hydrogen atom could have was negative 2.179 times 10 to the minus 18 joules, and that's the same energy that an electron wave would have if it's centered on the nucleus of the hydrogen atom. And so from the quantum point of view, this wave, this electron wave, this wave for an electron that's sitting on the nucleus of the hydrogen atom, this is the ground state of the hydrogen atom. In other words, a hydrogen atom in its lowest energy state has the electron trying to be at the nucleus, but because the electron is so light, it becomes spread out in space, and it actually extends well outside the nucleus of the hydrogen atom. And in case you're wondering, the first orbit, the ground state orbit in the Bohr model, would be right around here. And so the size of the electron wave is comparable to the size of the electron orbits that were in the model that Niels Bohr proposed for hydrogen. So here's another picture illustrating this first energy level for a hydrogen atom. And here, just to make things a little bit easier to see, I've shaded in the region of space that includes 90% of the electron wave. And so the electron wave has a spherical shape, and 90% of it falls within about 150 picometers of the nucleus. And this would be a standing wave. It's not moving anywhere. It's centered on the nucleus, and to make an analogy with the drum head, this wave would be analogous to simple motion of a drum head, just vibrating up and down. That's the lowest energy vibration of a drum head, and that corresponds to the first energy level of a hydrogen atom. Now, the second level of the hydrogen atom actually there are two types of wave that have that fall into that level, and one of those types corresponds to this kind of vibration of a drum head, where the the inner part of the drum head is vibrating up and down. The outer part is also vibrating up and down. They're out of phase with each other, and there's a some distance from the center where the drum head is actually not moving at all. So in that around that circle, there's no energy in that vibration wave, and the corresponding picture for the electron wave in hydrogen looks something like this. You've got a region of intensity close to the center, and then there's a spherical region where there's no intensity. That's called a node, and then beyond that there's another region of wave intensity, and so this is sort of a spherical equivalent of that wave pattern on the drum head. So this is one wave pattern that has that is in the second energy level for a hydrogen atom. Another wave pattern is analogous to this type of movement of a drum head, where one side of the drum is going down while the other side is going up, and here there's also a region where the drum head is not moving, where the energy of the wave is zero, and that would be along this line here. And in 3 dimensions, in the case of the hydrogen atom, the corresponding wave pattern would look something like this. You'd have a region on one side of the nucleus where there's wave intensity. There's a region on the other side of the nucleus where there's wave intensity, but there's a plane in between them where the wave doesn't exist. And so this pattern is, it actually has the same energy as that other pattern with the concentric spheres, but the geometry is different. And in the picture that I'm showing here for the electron wave pattern, it's the wave is oriented sort of along the y-axis of the atom. There's nothing special about the y-axis. You could just as easily draw the wave pattern oriented along the x-axis or along the z-axis. And in fact, all 3 of those are considered distinct wave patterns. And all 4 of those patterns on the right here would have the same energy. They'd be energy in the n equals 2 energy level for hydrogen. Now, when you get to the third energy level, there are 3 patterns of the wave, and these are referred to as sublevels in the third energy level. So one type of wave pattern has this sort of spherical shape, and there's internal structure that I'm not going to get into because visually it becomes very complicated. And then there's another type of wave pattern that where you've got wave intensity on either side with a node in between them, and there are 3 wave patterns that look like that. And then there's another type of wave pattern where there are 2 regions of space where the wave vanishes, and there are 5 distinct wave patterns in that sublevel. And you can extend these kinds of pictures to higher and higher energy levels. They begin to get visually very, very complicated. So this is as far as I'm going to go for now. But this gives you a sense of how the electron wave in a hydrogen atom is arranged in space. And in the next video, we're going to look at ways to describe these wave patterns and sort of break them into categories. And so that is what we'll talk about next time.